Hello everyone, welcome to IMS GATE Academy. I am Atul Negi and we are discussing our foundation course on fluid mechanics. In the last lecture, we have discussed the application of Bernoulli's equation, and in that we have discussed the Venturi meter. Okay, we discussed the each and every important aspect of Venturi meter. Hi Pragya. Okay, I hope all those important points regarding Venturi meter it is clear to everyone, right? Now, in this particular lecture, we will discuss some more application of Bernoulli's equation, like Orificemeter and Pitot tube. So these are the most important application apart from the Venturi meter, right? In dynamics part, you need to discuss regarding the motion of fluid, okay, and also the forces which are there in the fluid motion, right? So all those forces we are need to discuss. Okay, everyone. So like in the Venturi meter we have discussed, it is used to measure the discharge. Like in the same way, orifice also measure the fluid discharge. Okay. Now first of all, we will see the constructional details of Orificemeter and how to calculate the discharge formula. Okay. Basically, we'll see what is the discharge formula in the Orificemeter and how it is different from Venturi meter. What are the advantages or the disadvantages are there between Venturi meter and Orificemeter? Okay, because both are serving the same purpose. So we should understand what are the basic difference between Venturi meter and Orificemeter. Okay, so that we can differentiate. Okay, in this application I will prefer Venturi meter, or in this application I will prefer Orificemeter. Like that basic analysis you should understand. Okay, everyone. Now, so we'll start with the Orificemeter. So first of all, I will discuss regarding the basic detail, constructional details of Orificemeter. Right? See, in the Orificemeter, there is what a plate, sharp edge circular plate is there, in which a central hole is there. So this is the sharp edge plate which is placed in a pipe, and there is a hole in the circular plate. So like this is the front view. If I have to draw the let's suppose this is the front view. If I have to draw the side view, you will see a hole in the circular plate. Sharp edge circular hole is there. So in that circular hole, the fluid flow will be there. Fluid is coming here, and what is going to happen? It will move like this. Okay, suddenly the area decreases. And after that, again, retardation and expansion will be there. Okay, after this, immediate conversion part. So this conversion part will be there, and then after that, a diversion part is there. Now, if I talk about the basic difference, first of all, the constructional difference between Venturi meter and Orificemeter is there. We have provided a conversion part, we have provided a diversion part, and between them a throat is there. But in Orifice, there is no conversion part you have provided, no diversion part you have provided. So remember, these are the very important constructional details. What we have provided is simply a plate having a circular hole called as orifice. So what will happen when the fluid flows like this? Initially the fluid was like this, right? Because of this hole, a conversion part will be created within the fluid itself. A converging flow will be created because of this orifice, right? And after that, a divergent part you will see. A very important point, the area will not be minimum at the orifice. Area will be minimum at after some distance. That particular point is known as the vena contracta. Vena contracta is the minimum area within the fluid itself. During the fluid flow, there is a point at which the area becomes minimum. That point is known as vena contracta, and it is very much different from the throat. You should understand this point. Throat and vena contracta both will have a minimum area. That is correct. But that vena contracta formed within the fluid flow itself. Throat is what we have provided in the Venturi meter. Okay. Throat we have provided in the Venturi meter. It's not like vena contracta I have provided. It's not like I have provided vena contracta. Okay. So try to understand. This is what the experimental observation you will see. Area will not be minimum. It will be minimum some distance after the orifice. It cannot be minimum at this point, because see what will happen. See, there is no conversion part you have provided. Obviously, conversion part we have not provided. Earlier, like in Venturi meter, we have provided a conversion part. Then there is some throat. Then the diversion part we have provided. But in this case, there is no conversion part we have provided. So what will happen? Suddenly you will see the convergent flow here, and as it is passing through this orifice, so after some distance of the orifice, the area becomes minimum, not at the orifice itself. So if you provide this convergent area, obviously the minimum area you will find this in this throat only. Okay, but in this case, orifice will not be having a minimum area. After some distance of the orifice, you will see a minimum area. That area will be known as vena contracta, which is there within the fluid itself, right? The minimum area in the fluid flow. That is what the minimum area. Correct. So that is what the basic difference you should understand. So if someone says vena contracta and throat are same, no, both are different. Yes, the point is there, like both will have a minimum area. That is correct, but both are not exactly same. Both are different. Okay, I hope this point is clear to everyone. So now after when fluid flows this after this orifice, so obviously it will diverge like this. Diverge like this. Now obviously after certain distance the pressure again increases, and because of that adverse pressure gradient, you will see what? You will see the circulation and eddies formation. Circulation and eddies formation you will observe. Right? See. Circulation and eddies formation you will see. Circulation and eddies formation you will see. Right? Now because of this circulation and eddies formation, what is going to happen? The losses are going to happen. The losses will occur. Now if I ask you, the losses will be what? More in Orificemeter or in Venturimeter? What will be your answer? What will be your answer? Tell me. What are the losses? In which case the losses will be more? Venturimeter or Orificemeter? See, apply your mind. In the Venturimeter part, we have provided the diverging area. We have provided the diverging section. But in this case, there is no diverging section is provided. So what will happen? The losses you will see in this case, the losses in the case of Orificemeter is very high as compared to Venturimeter. That is important point you should understand. Okay. So losses will be there. A flow separation will be there because of the adverse pressure gradient. If someone asks you directly what are the reasons of this flow separations or this circulation or eddies, you should directly tell adverse pressure gradient is the main reason. Because of this actually it is happening. I hope this point is clear, right? Okay. So these are the basic details or constructional details you should understand. So Orificemeter will have a sharp edge circular plate which is having a hole. From that hole basically known as the orifice, from that orifice the fluid flow is coming. Okay, so fluid passes through that orifice. So area will not be minimum at the orifice, it will be minimum after some distance. Okay, because suddenly it is converging, right? Sudden convergence you will see here. Earlier, in the case of Venturimeter, we have provided converging part. In this case, there is no converging part. So how the area can be minimum at the orifice? So it will be area will be minimum after the orifice only. That is what you can observe, because that is the experiment we have done in our engineering also. So if you have done that experiment, you will better know about this thing. Like orifice you will see after some distance from the orifice. Because sudden convergence you will see. Okay, suddenly area decreases. Earlier area is this much, suddenly the area like this. Because of that only the area minimum you will find here, and this is there in the fluid flow itself. Okay, the minimum area you will find in the fluid flow itself. Correct. I hope this point is clear. Right. Now, as we have discussed regarding the losses also, losses are what more in case of Orificemeter, because there is no diverging part provided in the case of Orificemeter. So losses will be more. Now, if losses are more, can you just tell me which one will have more CD value, coefficient of discharge? Venturimeter or Orificemeter? That is what the direct question I am asking you. CD value, which device will have a more CD value? Orificemeter or Venturimeter? Please tell me, guys. Everyone, tell me what will be the correct answer. See, losses more in Orificemeter, basically it means it will have a low CD value, because what is CD represents? Last lecture we have discussed. Actual discharge divided by the theoretical discharge. CD value will be what? Very less as compared to the CD value of Venturimeter. So in the Orificemeter, the point that we need to remember, Okay, the point we need to remember is what? It is having a circular sharp edged hole plate. Okay, circular sharp edged hole plate. Right. Now, just think of like in the venturimeter convergent part, throughout divergent part. So some length will be required for the venturimeter to install in the pipe. When we want to install the venturimeter in the pipe, it will require some length. But in this case of Orificemeter, no length is required or very negligible length is required because you are inserting water, simply a plate itself, which is having a sharp edge circular hole. Correct? Shape of a throat is a small cylindrical shape, but vena contracta look like a circular shape. Vena contracta look like a circular shape. See, Pragya, you should understand. See, first of all, you should understand this point. Okay, so this is the one. Let's suppose your plate is having like this. Okay. See, this is your plate. Okay, this is the plate having a circular hole. So try to understand. Okay. Now the fluid which is coming out from this orifice will be what? The fluid which is coming out of this orifice, the circular shape, it will be, obviously it will be circular, na? The fluid is coming out from this small circular orifice, the fluid will be what? Looks like what? Circular shape only. Okay. So you should understand, this is what we are having, a circular plate sharp edge hole. Okay, correct. Now see, so we have discussed regarding this Orificemeter, sharp edge circular plate we are having. Okay, now second thing that I want to discuss here, so I will write it here itself, the point that I have to discuss here, the losses in Orificemeter the losses in Orificemeter are more as compared to venturimeter. Okay, and as a result you will observe CD value of venturimeter will be what? More as compared to Orificemeter, as compared to CD value of Orificemeter, because losses are what? More in the case of Orificemeter, so its CD value will be less. Okay, its CD value will be what? Less. Correct. That is one important point. Apart from that, see, as we have discussed a circular sharp edge, circular plate having sharp edge hole, there is an important coefficient. The coefficient that we need to remember here is coefficient of contraction. Coefficient of contraction. Now, what is coefficient of contraction? It is represented by CC. Okay, it is the area of orifice divided by area of vena contracta. Area of vena contracta, right? I hope the point is clear. So coefficient of contraction, which is equals to what? Area of orifice divided by area of vena contracta. That is what the coefficient of contraction we are having. Now apart from that, what are the other coefficients we are having? CD, that we have already discussed. Actual discharge divided by theoretical discharge, right? One more coefficient is there, that is coefficient of velocity. Which is represented by CV. So we can write CV like this. Actual velocity divided by theoretical velocity. And there is a one important relationship between all three coefficients, right, that you need to remember. It is like CD equals to CC into CV. Okay, so this relationship you should remember always. Very important, because in the examination they can give any one of the two values and they will be asking the third value also. Correct? So CD equals to CC into CV, right everyone? Okay. Now, so we have discussed regarding all the coefficient. Next thing that we need to discuss is the discharge formula. That is what the discharge formula we need to discuss. Okay, discharge formula we need to discuss. Or Orificemeter. Okay, for Orificemeter, right? Now see, what is the formula here? First, we will be writing the theoretical discharge formula. Okay, it is area A1, area A0. Not basically represents for orifice, right? Root 2 GH. H is the pressure head difference. Okay, everyone? A1 square minus A0 square. Okay, so where you should remember area of orifice, right? And this A1 is the area of pipe. Okay, so this formula you should also remember. Now if I multiply the value of CD, so I will be getting what? Simply the actual discharge. If I multiply the CD value with the Q theoretical, I will be getting the actual discharge. Okay, so that is what the theoretical discharge. So Q actual will write like this. Just multiply CD with the Q theoretical, A1 A0 root 2 GH. Correct? So this is the actual discharge formula. Right? So I hope the point is clear. So actual discharge formula, just CD you need to multiply. Let's suppose in the question CD value is not directly given, but they have given CC, coefficient of contraction, coefficient of velocity they have given. So we can use the previous relation that we have written here. The CD equals to multiply of CC and CV. If you multiply CC and CV, you will be getting coefficient of discharge. So see, like derivation part we have done in the Venturimeter, same kind of derivation is also involved in the Orificemeter. So that we are not doing, because already we have done for the Venturimeter, correct? So if you want to see the derivation part, you can just see the previous lecture of the Venturimeter, where we have done detailed derivation of the coefficient of discharge also, and this discharge formula, theoretical discharge formula we have derived completely. Each and every steps we have followed in the Venturimeter case, because those steps are again repeated in the case of Orificemeter also. That's why I'm not again repeating all those steps here in the case of Orificemeter. So that's why directly I've written the formula. Okay, you should understand, directly I've written, but if you want to see the derivation part, just see the previous lecture also for the Venturimeter. Okay, coefficient of contraction, this is what important that you should remember, area of orifice divided by area of vena contracta, and this is the plate. So basic point that you need to understand is the losses are more. Why? Because there is no diverging part that you have provided. Flow separation, in this case you will see more flow separation. more circulation, more eddies formation you will see in this case. But what is, if someone asks you what is the advantage of orifice meter as compared to venturimeter, you can simply tell, if you see the length of venturimeter, which is like very high, if you see, if you just compare with the orifice meter also, the length of a device for the venturimeter is high as compared to orifice meter. So it will not take that much length. Which one? The orifice will not take that much length as compared to venturimeter. Okay, because in the orifice meter simply a circular plate you need to install, but in the case of venturimeter, entire device having three parts, convergent part, throat and diverging part, all three parts combined to have some length it is having, so that you need to install in the pipe, so it will take some length in the pipe. But in the case of orifice meter, it is what very easy, just insert a simple circular plate having a sharp edge hole, simply you can put it and you will get the value of discharge. But the point is, the point that we need to remember, in the case of orifice meter, losses are more. Now you will be thinking, sir, how much losses? Any idea about that? Yes, just you can think of what is the value of CD in the case of orifice meter. From that you can easily understand. Okay, if I have to write the CD value of CD for orifice meter, if I have to write value of CD for orifice meter, it ranges from 0.6. Okay, around 0.6 it is there. Now compare with the venturimeter, it is around 0.97. So venturimeter is highly accurate device as compared to orifice meter. Highly accurate device. Venturimeter is a highly accurate device. You should understand this point. Why we are saying? Because of the value of CD. In the case of orifice meter, what is the value of CD? 0.6 only. Got it? Tell me guys, any doubts till now? Any doubts? So you should remember this range 0.6. Okay, 0.6 to 0.67, 0.65 like that. So approximately in the range of 0.6 it will be there. Okay, and one more point you can write it here, the venturimeter is more accurate device. Venturimeter is more accurate device as compared to orifice meter. So this kind of statement you can see in your MCQ or MSQs also. This statement they can use in the form and the questions also. Okay, more accurate device as compared to orifice meter. Correct, because the value of CD is what very high in case of venturimeter, around 0.97 or 0.98, but in case of orifice meter it is 0.6. Correct. Any doubts from the orifice meter, guys? Please tell me. Correct. Okay, now as in the starting of the lecture itself I have told you, apart from orifice meter we will again look for the next application part of the Bernoulli's equation, that is Pitot tube. Okay, we'll see what is Pitot tube and what we are actually measuring from Pitot tube, advantage of Pitot tube, how the Pitot tube works, all those things we are going to discuss in this lecture, right? So orifice meter is done. Now we'll discuss the Pitot tube. Okay, now see, Pitot tube. Now, so I will first of all draw the diagram here, and from the diagram itself you will be able to understand. Okay. Okay. Now see, so let's suppose some fluid flow is there. Okay, in the pipe there is some fluid flow. Now I have attached, let's suppose, a simple piezometer. Assume like I have attached a simple Pitot tube, a simple piezometer, not Pitot tube. Simple piezometer I have attached. Okay, like this. Now try to understand, very important point. Now as the fluid is what flowing here, as the fluid is flowing here, so let's suppose this is the point 1. I am assuming. So what actually this piezometer will tell us? Can anyone tell me what actually this piezometer will tell us? Piezometer will tell us the static pressure value. Static pressure value it will tell us. Static pressure value it will tell us, right? Okay, so let's suppose till here the, let's suppose it is filled till here. Okay, till here it is filled. Simple. Pressure at, yes, static pressure, absolutely Sandeep, correct. So static pressure it will tell us. Which device? The simple piezometer, simply. So I will be getting what is the static pressure at point 1 just by measuring this much height. Just by measuring this much height, I will be able to get the static pressure height. Now, second thing is what the Pitot tube we are having. Okay. Now I will tell you how the Pitot tube will look like. Now try to understand a very important point. Now, assuming the point, next point to be like this. Assuming this is our second point. I hope the point 1 and 2 is visible to everyone. Correct? Point 1 and 2. It is visible? Right? Now see. Better I will remove some dots here so that you will get to know all the points. Correct. So this is the Pitot tube I have installed. Now very important point. This point number 2 is a stagnation point. First of all, you need to understand what is stagnation point. The point at which the velocity of the fluid flow is what 0, that point in the fluid flow is known as stagnation point. So just in front of this Pitot tube, the point 2 is acting as a stagnation point where actually the fluid velocity stops because of this Pitot tube. Correct. Now what is going to happen when the velocity is what 0? What is the amount of, like, when the velocity is 0, what will happen to the kinetic energy? Where the kinetic energy is gone? But tell me this point, where that all kinetic energy is gone. If the velocity is 0, kinetic energy is 0, but where that energy is gone? The simple question comes in our mind, like where that energy is gone? It has been dissipated or it has been what? Removed from the system itself. So you should think of, like, velocity is 0, correct, I accept it. The stagnation point, velocity is 0, kinetic energy is 0. But where that energy is gone? My question is this one. Tell me, where that energy is gone? Now you will be thinking, sir, okay, that kinetic energy maybe get converted into some another energy. That is one of the possibility also, correct? That is the possibility, right? Energy may be transformed, na? That is what the basic thing that we have learned from the school also. Energy can change its form, it can get transformed into another form also. That is the possibility. So we'll see in what form it has been transformed. Now, just simply apply this. This is the Pitot tube. What will happen? The velocity of the fluid at point 2 is 0. Now, what will happen? Slowly the fluid will fill up. The fluid will fill up in this tube, in the Pitot tube. Okay, so assume like it has filled. Now what you will observe when you will do this experiment, now you will observe that it has been filled up to this point. Let's suppose up to this point it has filled, but you will observe a very important point here. The height up to which it has been filled in the Pitot tube, it is much greater as compared to piezometer. Are you getting my point? If you just compare the height of liquid filled in the piezometer and the height of fluid which is filled in the Pitot tube, it is what different. And what is that different? The height in the Pitot tube is what more as compared to static tube or simply piezometer. So why that difference came, and from where that difference come? Why the height is what more in the Pitot tube? That is what should be our question. Now when we are doing experiment, we should ask like why the height of fluid here in this case is what more as compared to this one. That should be our question. You should understand this point. Are you getting yes or no, everyone? So simply just by drawing the dotted lines, I will show you. Okay, now I will show you with the difference. What are the differences? Difference is this much. Difference is this much. Are you getting the point? This is the difference. Now, first of all, this much head is known as static pressure head, HS, or simply H naught. I will use the notation H naught here, not HS, because HS I will use for stagnation head. This H naught head represents what? The static pressure head. This much head is known as what? HS, which is representing stagnation head. Now I will tell you what is the kinetic energy, where that kinetic energy has gone. Now I will tell you. Just by applying the Bernoulli's principle, you will be able to understand. So applying the Bernoulli's equation. Okay, so here I will apply. Between 1 and 2. Apply Bernoulli's equation between point 1 and 2. I hope the point is clear. Now, if you apply it 1, simply pressure P1 by specific weight plus V1 square by 2G plus Z1 equals to P2 divided by specific weight V2 square by 2G plus then Z2. Now, it is what? Horizontal, so I can cancel out Z1 and Z2. Simply I can cancel out Z1 and Z2. Right? So it will get cancelled out. Now the point is, see. Okay, point is like V2 velocity is 0. Now what is there? P1 by W, that is the static pressure head at point 1. So I will represent with H naught plus V1 square by 2G. Correct? Whatever the height it is there, it is represented by stagnation head. Simply P2 by W will be the stagnation head HS. Correct? Now actually what happened, all of the kinetic energy has been transformed into pressure energy. That is the point. All of the kinetic energy has been transformed. Kinetic energy is transformed into pressure energy. That is the point everyone should understand. Correct? So kinetic energy is transformed into pressure energy because all of the kinetic energy has been what? Zero at stagnation point. So what will be there? All the kinetic energy suddenly converted into pressure energy. That's why this head is what? More as compared to this one. Now, if I have to calculate the velocity V1, I can simply calculate. V1 will be what? Under root 2 into G HS minus H naught. Okay. So that is what the formula you will be having. This will be your formula. Right, everyone? Correct? Everyone, tell me. Now, one more point you should understand. The difference of stagnation head and the static pressure head is what? The dynamic head. or the kinetic head. So this difference that earlier I was asking you, this difference is the this is what the kinetic head or the dynamic head, because this is static head here, this is the stagnation head here. So difference will be always the kinetic or the dynamic head. Okay, so it is what? Kinetic head. Difference of stagnation head and the static pressure head. I hope the point is clear. Next, just try to understand this. H naught static pressure head. Stagnation pressure head, correct? Our kinetic head is the difference of Hs minus H naught. That is the difference of stagnation minus static pressure head. This point everyone should remember. Correct? So I hope the point is clear. Where the kinetic energy is gone, it has been transformed into pressure energy. Simple. So it's not like energy has been dissipated or it has been removed from the engine or from the basically the Pitot tube, our fluid system. So energy always remain conserved. We should understand how the energy is transforming during the fluid flow. How the energy has been what? Transforming its form of energy transforming during the fluid flow. Are you getting? So during the fluid flow, you should understand the energy is going to what? Transform as the fluid is what flowing in any pipe or any open channel also. So that point we should understand. So energy always changes its form. So we need to understand how it is changing its form. Correct. So second, so we should mention here second as a stagnation pressure head, stagnation point. Okay, and we'll mention here okay, at a stagnation point velocity of flow becomes 0. Velocity of flow becomes 0. Very, very important point. So kinetic head is the difference of stagnation pressure head minus the static pressure head. I hope the point is clear, everyone. Now, can you tell me, if you are having only Pitot tube, can you able to calculate? Just tell me, will you be able to calculate the velocity of the fluid flow? Yes or no? Is it possible for us to calculate the velocity of the fluid flow with just a Pitot tube? Just tell me. See the Pitot tube. Can you tell me like what is the kinetic head? No, it is not possible. Why? In order to find the kinetic head, we should have the static pressure head. For that, we should have the piezometer or this static tube we should have. If we don't have this value, we will not be able to get this difference, because the Hs is the summation of static pressure head plus dynamic head or the kinetic head. We don't know how much amount of kinetic head is there and how much amount of static pressure head is there in stagnation head. So we should have the Pitot tube, along with we should have a piezometer also, so that we can easily find out the static pressure head. Without the static pressure head, I cannot tell what is kinetic head, and I cannot calculate the velocity of the fluid flow. Very simple point. Because in the interviews, they will be asking this question. Let's suppose you are having Pitot tube. Can you calculate the velocity of fluid flow? You will say, yes, actually we can calculate it, because Pitot tube is used for what? Measurement of the velocity. So actually it is what a trap that the examiner will create or the interviewer will create for you. He will ask you, because everyone knows like Pitot tube used for velocity measurement. He will give you Pitot tube. Okay, let's assume you have a Pitot tube. Tell me what will be the velocity. He will give you the parameters also. But is this possible for you to calculate the velocity of fluid flow with just Pitot tube? Not at all. You should understand this point, because we will just have a stagnation head, but I don't know na, from that stagnation head what is the amount of static pressure head, what is the amount of kinetic head. In total stagnation head, let's suppose this is 100 value. So out of 100 value, what is static pressure head, what is kinetic head, I don't know. So we should have this value H naught from the piezometer. Then only I can calculate kinetic head. So along the Pitot tube, we require the piezometer, so that I can calculate the static pressure head, and the difference of stagnation head and the static pressure head will give you the kinetic head, and from that velocity I can easily measure. Correct? Yes or no? Any doubts? Please tell me guys fast. Correct. Okay, I hope the point is clear. So this is the direct formula from which you can calculate velocity. Okay, but this velocity will be the theoretical velocity. So whatever theoretical velocity you have calculated. So what is the theoretical velocity you have calculated? 2 into g minus hs minus h naught. Actual velocity. Okay. Actual velocity you will calculate using the CV, coefficient of velocity term, right? So both the things you should have a clear understanding. Okay. Apart from that, I think all the points are what clear to everyone. All the points are clear. Correct. Any question? If you have any question, please ask. If you have any question in this Pitot tube, you should ask. Okay. Okay. Now this Pitot tube can also be used in open channel flow also. That is also there. This Pitot tube can also be used in the open channel flow. So I will just show you the diagrams here. So that will give you the better clarity. Now see, this diagram will give you the better clarity. Right? See. So again, static pressure you have calculated from this tube, simple piezometer tube. This is the Pitot tube you are having. In the Pitot tube, dynamic pressure or the dynamic or the kinetic head you can calculate, just because you have the static pressure head. Because of the static pressure head only you can calculate this much dynamic pressure. Because the stagnation head is the summation of static pressure head plus the kinetic head. Stagnation head is the summation of static pressure head plus the dynamic or the kinetic head. Simple. Now, apart from the static pressure head also, both things, two things are also there. There is one, you are having the due to weight of the fluid itself, first of all. Then second, due to the pipe internal pressure. Due to pipe internal pressure, this much is height, and this much height will be what? Due to weight of the fluid itself. Correct. So you should understand the points. This Pitot tube will help us. This Pitot tube will help us to calculate the velocity of the fluid flow only when we are having this static pressure head, which is again the summation of pressure due to the pressure which is their internal pressure, the pressure which is there in the pipe itself. So which is we are calling like due to pipe internal pressure. Second, due to the weight of the fluid. So static pressure head is the summation of two things, due to internal pipe pressure and due to weight of the fluids, weight of the fluid basically. So these 2 points you should understand. Okay. So this is point A, this is point B. So at point A, this much static pressure head. At point B, this much stagnation head. Take a difference. This one will be the dynamic pressure head or the kinetic head. Simple. So I hope this diagram will give you better clarity. Next thing. But always you should remember the point. Stagnation head. Summation of static pressure head plus the kinetic head. Static plus kinetic. Correct? So this point you should always remember. Next is what? In the case of open channel flow. Right? So I should mention here the point here. in open channel flow, right? In open channel flow. So in open channel flow, a very important point, Adarsh is asking some question like BTech Mechanical Engineering branch in third year in AutoCAD for if I will design MTech. Yes, others, that will be a very good option. Like if you are thinking of doing AutoCAD and CAD/CAM, basically some softwares related to design, if you do it in the BTech third year or final year also, that will be good and it will help you in your MTech if you are thinking of doing MTech in design. So that will be a good thing because it will help you. Initially it will help you, right? So most of the students will learn those softwares in their MTech also, but if you learn those softwares in the engineering itself, then it will be a very good, okay, you will have an edge, you will have an extra edge over other candidates also, right? And more you will be involved in the projects. That will be a good option. Okay, Adarsh, I hope it is clear. Now coming back to the topic, like in open channel flow, how the Pitot tube will work. See, this much head, see again, let's suppose this is what we are having as. So free surface, I hope everyone remember the free surface point. This is the symbol of the free surface. Now this much will be due to static pressure, this much will be due to static pressure, and this much will be due to dynamic pressure. In open channel flow, I don't need any piezometer. I don't need any piezometer because this much head is itself the static pressure head. Always the static pressure head will remain same. Always the static pressure head will remain same. But whatever height apart from that you are getting, that is what belongs to the kinetic head that gives you the velocity of the fluid flow. Correct? So you should understand in the open channel flow how it is different and how it is different in the pipe flow. Both are different. Because in the open channel flow, you can directly measure the static pressure just in a single Pitot tube itself. You don't need again another one more tube like piezometer like we require in pipe flow. That we require in pipe flow, but it is not required in open channel flow. That is the important point you should understand. Correct, everyone? I hope the point is clear. So this is the static pressure and this is what the dynamic pressure. So let's suppose the length is what given. You can easily measure it. Correct. And whatever value you will be having of this much, this is belonging to, this one belongs to what? V square by 2G. Simple. Correct? I hope the point is clear, right, everyone? So open channel flow also we have discussed. Now, a very good question that we'll discuss regarding venturimeter that was asked in GATE examination. That was asked in the GATE examination. Okay. So in 2021 they've asked this question. In 2021 they've asked this question for civil engineering. So everyone should try and tell me what will be the correct answer. Okay, everyone should try and tell me what will be the correct answer here. Tell me, everyone, please try and tell me what will be the correct answer here. A very simple, straightforward question they've asked from the venturimeter. So this is what venturimeter they've given, a vertical venturimeter they've given. Okay, right? Manometer fluid is also given, mercury. Manometric deflection is what given 15 centimeter. So I will write down first of all the given details here. Whatever the data given in the question directly, first of all I will write all those points. Venturimeter as shown in figure, not to scale, okay, is corrected to measure the flow of water. Okay, correct. Pipe of vertical pipe having 20 centimeter dia. So dia of pipe they have given, that is 20 centimeter. Correct. G value 9.8 we need to take. Deflection in the manometer is 15 centimeter. So usually I will take notation of x for manometric deflection. That is given as 15 centimeter. Okay. Okay, flow rate they are asking. Remember LPS, liter per second they are asking. Round off to 2 decimal places, considering no loss in the venturimeter. Correct. So no losses they have mentioned. So I will directly use the theoretical formula. The theoretical formula I will be using because no losses they have mentioned. We don't need to consider any losses. Throat dia 10 centimeter. Dia of throat. Okay, all these points are given. Now, very important point. Manometric fluid is what? Mercury. Simple. Direct formula we remember, everyone. I hope formula everyone remembers. A1 A2 root 2 GH under root A1 square minus A2 square. Now, in this formula, I hope everyone remembers what is H, pressure head difference. Pressure head difference, right? And what is the formula that we have used directly to calculate pressure head difference? I hope everyone remembers. In order to calculate pressure head difference, direct formula we have derived in the venturimeter last class. Direct formula I have derived for this value of H. It is manometric fluid density divided by density of fluid minus 1. Or I can take the specific gravity also, right? So H value you can directly calculate 0.15 because 15 centimeter is the deflection. 13.6 I have taken specific gravity I am taking, not the density, because again same thing it will be there. Okay, what they have mentioned, water they have mentioned, right? So for water specific gravity will be what? 1. So from that I can directly calculate what is the value of H. Very easy for us, correct? A1 A2, A1 you can consider the area of pipe, A2 you can consider for the area of throat. Very simple. So H I have calculated, A1 A2 I know area of pipe because dia is already given, A2 area of throat. Okay, all the data is already given. H you can calculate from this one. A1 A2 already given because dia is what given, pipe and throat everyone is given. Everything, let's suppose this I'm considering D1, this is D2. Okay, so D1 D2 clear. Area we can calculate pi by 4 D square. Just put all those values and tell me what will be the final answer of discharge here. Tell me, direct straightforward formula based numerical they have asked from this venturimeter. Everyone please try and tell me what will be the answer, and please remember they have asked the answer in liter per second. So answer we are getting in meter cube per second, the discharge, that we need to convert into liter per second, right? Tell me what will be the answer, guys. Please try it fast. Okay, everyone please try and tell me what will be the final answer here, because it's very simple, na? Okay, one more point regarding venturimeter you should understand, like in the given question, the venturimeter is there in a vertical pipe. The pipe can also be inclined at any angle. Remember the point, the formula that we have written for pressure head difference, it will remain unchanged, or whatever calculation we have done, it will remain unchanged with respect to orientation of the pipe. Whether pipe is inclined, vertical, horizontal, the formula will remain unchanged. Remember this point. Never think like formula will get changed. No, just see the derivation part. Okay, everyone. So whatever the orientation of pipe is there, we don't need to worry about the formulas of venturimeter, because as in the derivation part we have taken the for horizontal case. So if even if the pipe is inclined or whatever angle is there, let's suppose this is vertical also, we don't need to worry because that formula will be applicable for all of the cases. It is all the formulas are what? Independent of the orientation of the pipe. I hope that point is clear to everyone, right? So you should understand this point, okay? Don't worry about whether it is vertical, inclined, horizontal, no matter. What is the orientation of pipe? We can directly use the same formula, okay? So finally, if you apply, see, approximately 49.4 liter per second will be the answer. You can just cross check also. Whatever answer you are getting, just cross check with this answer. 49.4 liter per second will be the correct answer for this particular numerical. Yes, 49.4 is the correct answer. Okay, everyone. I hope Orificemeter is also clear. Pitot tube is also clear. The basic fundamental equations that we have applied in the Pitot tube, it is also clear. What is stagnation pressure head, what is static pressure head, and what is kinetic head. So you should understand the static pressure head plus kinetic head gives you the total stagnation head. And in order to calculate the kinetic head, you need to subtract the stagnation head and this static pressure head. In the pipe flow, simply if you have the Pitot tube, you cannot simply calculate the velocity of fluid flow or the kinetic head, because from the Pitot tube, what you are getting? Only the stagnation head. From the Pitot tube, what is the output you are getting? Whatever height is there, what actually that height represents? Stagnation head. So what I will do with the stagnation head if I don't know or if I don't have any information regarding the static pressure head and the kinetic head? So remember this point. In the pipe flow, simply if you are having the Pitot tube, you cannot tell what is static pressure head and what is kinetic head. You need one more tube, which is piezometer, from which I can calculate static pressure head. Then after measuring that value, finally I will subtract the static pressure head from the total stagnation head. Then that difference we will having, whatever the difference we will be having, that difference will give us what value? That difference will give us the kinetic head. So remember, they will ask you in the interviews also, with the Pitot tube, what you can get, which values you will be getting? Only the stagnation head, not the kinetic head. For that you need separate piezometer. But in the case of open channel flow, only Pitot tube is required. Correct? So I hope that those diagrams that I have shown you, it is what clear, right? This is for the open channel flow and this diagram for the pipe flow. So I will mention here pipe flow. Correct, everyone? So due to internal pipe pressure, this much height and this much height will be due to weight of the fluid flow. Total static pressure head, total stagnation head, and the difference is dynamic pressure or kinetic head simply. Correct? So I hope all those basics point of Pitot tube and this Orificemeter is clear to everyone. And we have covered almost all basic important applications of Bernoulli's equations. Correct? I hope you have enjoyed this lecture, and if you have not watched the previous lecture of the Venturimeter or the derivation of the Euler's equation from which we have derived the Bernoulli's equation also, please watch those lectures also, because those lectures are the basic fundamentals of fluid dynamics, entire fluid dynamics, right? Okay, everyone, thank you so much, and we'll meet again in the next lecture with a new topic of fluid dynamics. Thank you so much.